Hello, everyone, and welcome to our first webinar of the day and the last webinar of the internship. I am Mohammed Al Zajjali, petroleum engineering student at University of Oklahoma, and it's my pleasure to be your moderator for this amazing webinar. Before I start introducing our speaker of the day, on behalf of the team of the internship, I would like to thank all of the students, professors, and engineers who participated on achieving the success of this internship, and we hope our efforts were blessed to help you gain the knowledge. And I would like to thank sponsors, Marietta College, SPE Egypt section, and BioPetro for being a great sponsors of this internship. Finally, I want to thank and appreciate all the team members who worked hard, and special thanks to our Dr. Ahmed Al Jarhi for the honest efforts presented during this internship. Our webinar today is about Introduction to EOR Polymer Flooding, which will be presented by Engineer Mostafa Kortam. Engineer Mostafa Kortam is a senior reservoir engineer working for a petrol company, graduated from Cairo University in 2008. His background and interests are in well stimulation, reservoir management, enhanced oil recovery, and field development planning. He is currently preparing a master's degree in petroleum engineering from Cairo University. It's our pleasure to have you today, Engineer Mustafa, and the mic is definitely yours.
Thank you, Mohammed, for your intro. It's really a long journey from starting the internship till ending with today's webinar. So the seminar and the session of today also represent the end or the end cycle of any typical oil development that undergo several cycles of the development strategy. So it's represented the tertiary and the last development cycle. So it's pretty aligned with the end of our internship. So going directly to our discussion that is related to the polymer flooding, as we stated, that represents the last cycle of any oil field. So with the introduction, so just to start with the deficiency of any water injection and that would result from the water flooding after reaching the mature stage of the water flooding or the water injection, ending with a low operating production that comes from the producer wells, along with a high production rate that represents the ending of the second life of the reservoir, and it being illustrate and demonstrate that there is some amount of oil that unrecoverable, which should be produced. Such kind of oil that was not recovered by the secondary recovery as really a significant share of the oil, and that may impact of losing some of your reserves. If you remember the bi-maturity chart where it was explained before, the major part of the oil is being lost and as being unmovable and unrecovered, by which such effort should be exerted in order to unleash and unlocking this missed potential and these missed reserves. So this opens the key for the EOR application, as we were explaining before. This kind of unmovable oil or unrecoverable oil that should be moved and produced and flowing owing to the primary or the secondary recovery comes from a two issue or two elements of the any water injection project. So as we addressed before, the main reason of having this situation and the practical characterization is attributed to the efficiency of the water injection. So it's all about the efficiency. Such issue comprise two parts, the displacement part and the conformance or the volumetric sweep part. So leaving some oil part within a pore space is one of the problems that would result from inadequate displacement efficiency, and leaving some of bypassed oil also one of the things that would result from inadequate volumetric efficiency. So residual oil is a signature of the displacement, and bypassed oil is a signature for volumetric efficiency. To address each part in details, hereby some what we are calling it a volumetric or macroscopic efficiency that take place on the macro scale of your reservoir. So the controlling element of this issue is that what we are calling it the mobility ratio. The mobility ratio simply is a term that measure how much the water is more mobile than oil, and it can be either faster than oil, and this in case of the mobility ratio are greater than 1, and it might be slower than the oil, at which the mobility ratio or the calculated mobility ratio is less than 1. So it's an easy parameter that can be calculated using the oil viscosity that comes from the BPT analysis, and combining it with the utilization of the relative permeability data, where we are picking the relative permeability at the end points. So we are choosing the KO over here, and we choose the KW at the SO residual, the higher effective water permeability. So this value of the permeability, along with this value of the permeability of the oil, are being employed and embedded within this equation in order to generate and obtain the mobility ratio. So in case of we found it, the mobility ratio is greater than 1, so it means that the water is moved faster than the oil, and that comes either by having a higher water viscosity and less oil, water viscosity. So this would produce that kind of flow, where the flow on the areolar scale is irregular and non-uniform, that lead to those part of bypassed oil. And same time, in the vertical scale also, it causes irregular and displacement on the vertical scale. So it causes on the impact on the vertical efficiency and on the aerial efficiency. While if the mobility ratio is less than 1, this may produce an unfavorable mobility, and the mobility ratio that is moving with the energy and the viscosity of the water that are closer to the viscosity of the oil. So we are obtaining a uniform and gentle flood front and a semi-uniform distribution in over the vertical scale of the reservoir that is being subjected to water flood. So simply, as it appears here, the mobility ratios at greater than 1, fingering and channeling is causing insufficient vertical and irregular flood pattern that take place on the aerial scale. The combination of those two effects would yield to have this performance after several bore volume injection. So you have to inject your reservoir at 5 times the volume of your reservoir in order to get that value of recovery of recoverable reserves, which is still very far and beyond the effective mobility ratio, which would result from the reservoirs that has a condition of a lower oil viscosity and a greater oil permeability with respect to the water. So the condition where it shows a good mobility and a mobility of water is closer to the mobility of oil or maybe less, we would achieve a good result by just displacing our reservoir with 1 time. We would obtain a greater recovery over the one that has or suffering from a poor mobility ratio. So moving to the second part of and the second class of the injection efficiency, which is known as the microscopic efficiency or displacement efficiency, that we explained it talk on the bore scale size, not on the reservoir size. So it's founded as a result of leaving a remaining oil that can be moved, and that oil that is trapped and entrained within the bore scale and the bore and the throat of the bore system the water that is should displace this oil out of these pores or find its way to bypass and to move around these droplets and these fractions of oil and leaving the residual oil that had or that impact or had an influence on the ultimate recovery factor. So the controlling element of this efficiency is what we are describing as a residual, as a capillary pressure. So the microscopic efficiency lead to have a great residual oil saturation that depends on the capillary number. So what is the capillary number states? It's just a ratio as well, but that ratio is not a ratio between forces. The viscous force that is responsible of displacing the oil with the force that resulted from injecting the water over the capillary force, that the forces that resulting from coexisting of two different fluids within the rock. So the presence of oil and water would establish a capillary forces, and there is some an interfacial tension would be resulted with the presence of two different surfaces and two different fluids. And with the effect of the mobility as well, we would have this, what we call it, a capillary forces. So the capillary forces simply is the forces that result from the coexistence of two different fluids, while the viscous forces is a force that resulted from a displacement of a fluid to another fluid. So simply, there is some a relation between the capillary number and with the residual oil saturation. So by increasing the capillary number, which means increasing the viscous force and reducing the capillary force, we would have a lower residual oil. So a higher capillary number will minimize the amount of residual oil that is being trapped over there, while the opposite is right. The higher capillary number, the lower capillary number, it would produce a much more oil that is being trapped and entrained within the pore space. So the outcome of the signature of the capillary number is, and the reflection of having a less residual oil is clearly obvious from the having a higher and a more prolific and a more rich oil recovery would be gathered at the end. So with this kind of lower residual oil, you would have at the same time a greater oil recovery because there is no more oil is left behind. So in short, we should try to increase the capillary number as much as we can. So in order to give a more explanation, here some research work attempted to understand the effect of capillary number of the displacement efficiency. So utilizing an advanced simulation technique that is used to show the flow through a micro model with different three capillary numbers. The pores are originally filled with the blue wetting phase. The blue now here is referring to the oil. So that part is the oil, while the displacing fluid is water and is non-wetting. So they are trying to mimic the oil wet system, where the water is trying to displace and to inject toward the oil in order to achieve a displacement mechanism. So at that time, with a different capillary number, that is the initial part of the examination of this of the test, and that is the end where the water, the red one, is getting out as an effluent from the part of this piece of model. So at that time, the higher capillary number would produce a much more oil, the blue one that already has been displaced out. And most of the piece is showing with the red one, indicating that is the water has displaced most of the oil. But while by decreasing the capillary number, we would have a different behavior, that we have some bypassed oils that are left behind, and with a very low capillary number, where the capillary forces are more dominated than the viscous forces, it would generate this kind of inefficient displacement. So the main effort or the main task now is how to increase the capillary number. And again, the viscosity is a key factor here. So it should, by increasing the viscosity, would improve and will raise the capillary number, and increasing the capillary number would achieve a greater and effective displacement. Also, we could think to minimize or reduce the interfacial tension and the capillary forces, that by decreasing the capillary forces, we are going to maximize the capillary number, and in turn, it would achieve the greater efficiency. So remember that the viscosity were ruling in the volumetric sweep efficiency, and there is also a rule in the capillary number that is a factor that rely on which the microscopic and the displacement efficiency rely on. So this slide show how can the polymer helps us. So simply by having or by introducing the polymer into the reservoir, we would increase the water viscosity, and at the same time also reduce the water permeability, and ultimately we can improve vertical and aerial efficiency, as well as we are increasing, or we are assist in increasing the capillary numbers, that in turn it has an impact on the microscopic efficiency. So rather than having the water that is being fingered and moving with this irregular pathway towards the oil, would have a stabilized behavior, and you are trying to raise the mobility of the water, since you are injecting a heavier and a viscous solution. So this would minimize and neutralize the mobility differences between oil and water. The same is taking place in the vertical scale. By just the water injection, this kind of fingering and channeling would be minimized by introducing the polymer, where the mobility ratio become closer to the unity. So the incremental oil recovery, so this is what, in short, is the polymer flooding has an additional improvement on the normal water flooding, delivering a higher oil recovery, since the water flooding has ended with this recovery factor. If you remember, the extrapolation of log water oil ratio to the economical limit can lead to the ultimate recoverable reserves. The polymer flooding improves the productivity of your reservoirs by having with a particular water oil ratio a greater recovery factor, and in turn improve and maximize the ultimate recovery factor and the efficiency of the overall injection. So now we are moving to discuss in details about the polymer flooding. These statistics was surveyed in 2016, where there are several numbers of projects that rely only on the polymer flooding, because the polymer can be mixed with either surfactant or any other of EOR applications. So it showed there is some several and many cases and applications, successful applications that are being utilized and undergoing the development of their fields using the polymer flooding. Worth also to point out that the largest current polymer flooding project is in Docking field. It's in China. And there is about 220,000 barrels per day as an incremental oil production that resulted from the polymer flooding. Also, there are about 85% of the field application use the polymer as a powder form, while the rest is using the 15% is using the polymer injection in a liquid form. So, giving some clues and a general description about polymer flooding that is used in the practical environment. Firstly, the viscosity of the polymer is distinguished by the polymer concentration rather than centibars. So it's just easy to describe it as ppm, not in the centibars. So if you are saying we are about to inject 50 centibars, so it should be described as, for example, a 200 ppm concentration. It's a well-known and famous relationship that generate at a corresponding ppm the corresponding viscosity of the polymer solution. So the people would rely on the ppm rather than defining the injection or the viscosity of their injection by the centibars. The typical range of the polymer that is used on the majority of the polymer flooding application is from 250 to 400 to 4,000 ppm. So most of the application are lying on this range. The mobility ratio in the reservoir is varies from 2 to 300. So over the 300, there is odd application that may achieve improper or a good performance, and less than 2, I think it's doesn't need, because it becomes closer to the 1. The polymer injection amount is being described as how much pound of polymer is being used by acre feet. So this is a typical range that is most of the fields are operating with, from 100 pounds of acre feet. So you can multiply your reservoir volumes, or how much acres, and with times the vertical. So this may require, or may indicate, utilizing this range, how much pound of polymer would you need. The polymer solution slug volume. Now we are talking about the polymer slug volume, aside from how much ppm is being used. So either 0.2 till 0.8 from the bulk volume. So most of the operators are working within this range. The additional gain on the recovery factor as an oil in place varies from 5 to 35, depends on how much polymer is being injected, and also in the efficiency of the polymer itself. And the proper design of the polymer also can maximize and lead to a greater number of original oil in place, as we are going to discuss. The molecular weight of the polymer varies. Most of the range is from 3 to 20 millions of molecular weight. The average annual consumption rate for a pilot, if you are just working with 1 or 2 wells, is just from 100 to 600 tons per year. But in the case of there is some full field extension, several wells and the different reservoir are being undergo a polymer injection, it may require the 1,000 ton till 160 ton. Of course, you are expecting that this is the value for the decking field, the largest polymer flooding field. So here, like what we are doing, we are getting a different type of polymer in order to estimate the concentration, or for a different or a particular concentration, how much is the resulted viscosity. So this is like a signature of any polymer type, or any polymer material that is used for EOR, is to have the concentration versus the viscosity. But this depends on the temperature and the shear strain is being applied. So it has to be distinguished either by the temperature or shear strain. That's what we are going to point out. So what are the types of polymers that is commercially available for the EOR, and what is the common types that is widely used? There is a polysaccharide group, and there is a polyacrylamide group as well. There is some cellulose material, and this is the formula and different types of polymers that can used for the polymer injections, belongs to the cellulose types. And there are some other polymers that are frequently used, but with a little scale. The most dominant and famous polymer type is the hydrolyzed polyacrylamide, according to the good features that it offers by this type of polymer. Also, there is the basic differences between or among those types of polymers that can differentiate between the performance of a polymer from the other is those kind of key parameters. So the mechanical degradation is a measure how much is the degradation and the losing of the polymer viscosity and the polymer efficiency that take place during the mixing and during the flow through the choke valves and the flow line restriction and the wellhead and so on. Also, it is a mechanical degradation can be happened in the sand face and across the perforation. Also, the thermal degradation is can differentiate and show up the differences between each type of the polymer, and they can rank the polymer according to how much it withstand with a different temperature ranges. The biological effect that comes from the bacterial attack. Also, there is some variety of all those kind of polymers according to its efficiency and its effectiveness to withstand and to undergo a particular bacterial activities. The chemical stability and also the salinity playing a role in affecting the efficiency and the performance of each type of those polymers. So any type of polymer that degrades has or undergo a degradation causes a change of its solution, and it impact on reducing the viscosity of the polymer. So it may convert it from a very viscous solution to a lower viscous that is closer to the water. So at the end, it didn't help by increasing this kind of efficiency of the water injection system. So based on the above discussion and the above explanation, it must be considered effectively the utilization of the polymer in the reservoir conditions that to mimic the reservoir temperature and the reservoir shear strain and the reservoir salinity as well. So the viscosity of the polymer solution, as we are knowing, increasing the viscosity is the relation, the famous relation between the viscosity and the concentration. So that is a greater or higher concentration, while that curve represents the lower concentration. So increasing the concentration of the polymer, of course, reflects the increase in the viscosity. But there is another factor that has to be considered, that you have to understand which condition you are measuring the viscosity. Is it on which particular shear strain? This is an example of different shear strain that can represent a particular condition of flowing the polymer through the journey from the mixing unit of the polymer till the reservoir. So if you have you are considering that shear rate in your system, so that will be the viscosity of each particular concentration. If you having a higher shear rate, that will be the case. If you have a less shear rate, so you may have the fancy to have a good performance of the viscosity with a less concentration, and even you can get a greater concentration with a high concentration of the polymer. So the polymer stability investigation, there are several experiments that is being used, and as you see over here, there are some examples of inspecting the polymer stability by conducting different tests to evaluate the performance of the polymer. So the mechanical degradation, in case if you have different polymers that has a different molecular weight, but this molecular weight have the same viscosity or initial viscosity of the same or of the higher molecular weight. So by the time you may expect some degradation in the polymer, the time of the test. The higher molecular weight offers a great and reduction and the deterioration in the viscosity. So it's very sensitive. Opposite or conversely, the lower molecular weight is less sensitive and show a basic no change on the overall viscosity. That's why some people would prefer to choose a lower molecular weight in their polymer flooding applications, in case of it have the same efficiency and can deliver the same viscosity that is the greater molecular weight can offer. The effect of the temperature, definitely increasing the temperature, this the viscosity of a different concentrations with the different temperatures. So the temperature here has been reduced for the 1200 ppm, and the same story for the 800 ppm, where the increasing the temperature would decrease the viscosity at a particular shear strain or a particular shear rate. Shear strain and the shear rate have the same meaning. Effect of the salinity: by increasing the salt content, we would influence on the viscosity and the generated viscosity, so it would adverse the viscosity. So increasing the concentration will reduce the viscosity of your solution. The effect of the chemical and biological degradation: if you are having this viscosity, or this example showing different types of polymer solution and the different type of polymer material. The first blue lines and curves belongs to two types of polymer that have a good capability to withstand the biological and the bacterial attack, while the red curve polymer types having a less strength regarding the biological activity. So it's the biological and the bacteria would reduce the efficiency of the viscosity over just a few days. So again, we should inspect and investigate the polymer and doing this kind of comparison and see the sensitivity of the polymer across different conditions and different situations. Now we are moving to one of the most important and one of the, it's really the most important behavior of polymers that must be carefully understood. In a simple way, it demonstrates the effect of the mobilizing the polymer through the reservoir. And since the polymer passes with a higher viscosity, so it will offer a higher differential pressure and the higher pressure that is required to mobilize the polymer through the bore system. So starting from that point, that represents the pressure required for mobilizing the water. If we start the polymer, we would have a build-up pressure and increasing the differential pressure across the core plug in order to mobilize the polymer through the bore system. So that pressure, the rise up in the pressure is owing to the fact that the polymer have a higher viscosity system. So we're reaching the stabilization. At that time, we have a stabilized performance of passing the polymer through the bore system, and the additional pressure drop that resulted to mobilize the polymer over the water called a residual factor. So simply, the residual factor is the ratio between the injection of water over the injection of the polymer. Later, if we displace the polymer with the water, it should not, or it can't be returned back again to the original state. There is some residual and some differences. So this kind of offset is what we call a residual factor, which represents the mobility of the water after the polymer respected to the mobility of water prior to the polymer flooding. And the additional increase in the differential pressure or the restriction or reduction in the mobility of water that occurred after passing the polymer is resulted by what we call adsorption of the polymer on the grain surface and the mechanical entrapment of the polymer within the small pore throat. So at that time, an observable reduction in the pore size and the porosity system and the pore throat would impact on the permeability of the rock. So the water that will flow following and post the polymer will face a different situation that was not existed prior to the polymer, because there is no impairment and entrapment and the absorptions on the system, and it was fluid easily with the poor system. But now there is some change and some difference that has happened permanently that lead to reduce the injectivity of the water and the mobility of the water. That's what we call it a residual resistance factor. So there are also differences in the polymer performance, and each polymer exhibits a different residual resistant factor. It depends on the type of the polymer. The biopolymer or polysaccharide, the polysaccharide material offer a less residual factor and a less resistant factor, while the polyacrylamide may offer a greater residual factors. But it was conducted on two different temperatures. So from here, you would find that there is some residual factor and the residual resistance factor as completely different between different types of polymer. Also, the temperature play a great role on the residual factor and the reservoir resistance factor. So conducting the experiment on a temperature 120 degrees Fahrenheit differs completely if it was conducted on 180 degrees Fahrenheit. So any of a polymer injection fields that utilize a powder unit has a standard scheme that contains those following items, where there should have a storage for the material of the polymer, the polymer powder unloading system, either by fork or some machines to unload the bags of polymer in order to move it into the silo. The powder silo is controls the amount of the powder polymer that is being moved and disposed into the tanks or those units, which we are calling it a polymer slicing unit or a polymer solution preparation. And the task of this unit is to prepare a thick polymer solution. Then it mobilizes it to what we call it a maturation tank to reach a stabilization or a stagnation in order to obtain an effective thick homogeneous polymer solution. So it required some time. Then another thing by our passing through the polymer metering pump that responsible to deliver the thick polymer solution into the mixing unit, where is an additional dilution is taking place to the particular designed solution and concentration of the polymer that, as we explained, that range from 400 or 250 till 4,000 ppm. So there are two steps: preparing a mother solution and a thick solution that has an order of several thousand of ppm, then dilute it again to return and to reach to the level of the designed polymer injection into your reservoir. Then we flow it through a polymer injection pump that is responsible for injecting and delivering the polymer solution to the wellhead. So now we are moving to a real field example where we are going to review the steps that is taken for designing a polymer flooding system. So this is a field in a Miocene age that locates in Egypt. It's in Gulf of Suez area. It's a sandstone reservoir. From the structure map that it's showing, this is a shale boundary, and there is a dipping indicating, and the dipping is going on that direction. So that is the upper part, and that is the lower part. This representing the aquifer, and this is the oil-water contact. There is a water injection that started at 2001. It's a peripheral water injection. The pressure is maintained above the bubble point pressure. The strategy is to place the producer well on the upper structure on the oil bank and place the injector well on the down structure in the oil water contact. So it's simply it move, and it's a typical example of peripheral water injection on the edge water. The injection was distributed from all surrounding and circumference of the field to allow an adequate aerial efficiency. The area of this part of the field is about 1,100 acres. So the drainage strategy, the field achieved an actual recovery factor or current recovery factor, or the recovery factor at the moment of the starting the water injection, just at 20% or 21%. There is some variety in the permeability that varies from 20 to 300 millidarcy. The porosity is 15. The viscosity, it's a viscous oil with 20 API, and the viscosity values is 8 centibores. The salinity is high, is 220,000 ppm, and there is a significant amount of hardness material. So the weak aquifer that acting in this reservoir requires a start and the commence of injection that was designed as a 3 peripheral injection in this field. With the high oil viscosity and the heterogeneous system, where it would generate a layering effect. The calculated mobility ratio was about 6, so it is unfavorable at all. If it's an example of a production from one of the wells, so the red one here is the production rate, the gross production rate or total production rate. The blue curve is the water cut, and the green one is the salinity. And that part of the chart represents reservoir pressure. It maintained almost constant most of the time since the start of the injection, and that was the effective management of the voidage replacement ratio to keep it closer to the unit. But the problem is with the response and the performance of the water cut was a little bit annoying, since the water breakthrough was took place in a quicker time, in addition to the oscillation of water cut and the frequent change of the water cut and the water production would imply a perception, and would deliver the perception that is you are dealing with a heterogeneous system and there is some aerial efficiency. So once the water arrives to the oil part, an additional oil with the course of the injection is being produced. It's something that is typical to the performance of that we reviewed in the first part, on the first section of the discussion, where we have this illustration. As the water reaches to the producer, with the course of the injection, with several injection volumes, you may produce and reinforce some of oil pockets to be produced and flowed to the producer well. And that what cause a gradual change and gradual rise up in the recoverable oil, but it required a longer time and much injection of the water in order to support and achieve the greater or the desired recovery. So return back to the chart. So having a chart on that way and have this oscillation, it can demonstrate existence of an aerial efficiency or a presence of deficiency in the aerial scale. So reviewing the reservoir pressure, that is the decline of the reservoir pressure since the aquifer is weak, and there was a period where the field was not producing effectively, and with the start of the water injection at 2001 and a rise up in the reservoir pressure, at the end it ended up with a wide range of the reservoir pressure, and some area of the reservoir are closer to the bubble point. And this is a famous performance and a famous problem that resulted from the peripheral water injection, as we discussed in the session of the water injection. It would have a great pressure gradient and the pressure contrast between the producer wells that are opposite to the injection and the well are far on the crystal side and far from the injection line. So this the reservoir pressure itself requires some improvement in order to rise up the production the pressure of the producer well are far from the injection. So reviewing and having a look on the petrophysical behavior and the petrophysical evaluation of the reservoir, it has basically two layers, and those two layers having a different porosity and a different water saturation, and even they have a difference in the pressure. So nevertheless, quality differences and the differences in the porosity, there is some differences also in the pressure values. It is slightly differences, but there is still, and that's what was discovered by recording on a pressure point. The shale is confirming as a barrier or a vertical barrier between those two sand bodies. A BLT was conducted in one of the injection wells of that reservoir. We discovered that is only 30% of the perforated interval receives the all amount of the injected water, and this due to that there is some vertical differences and the vertical discrepancy between the permeability of each layer. So there is some vertical heterogeneity on the injection wells, and from the injection part, initially the injection does not cover the whole interval of the reservoir, but most of the water goes for a particular strata and a particular layer rather than the other two parts of the reservoir. This is the first layer, and that is the second layer. Even within the first layer is not uniformly flooded across the first layer, but just the bottom part of the first layer or the upper layer, while the lower layer kept unswept and with no effective injection. So this is a sign for a poor vertical sweep efficiency, but this is the case in the injector well. What it will be the case from the production well, as we were explained before, by having the plot of log water oil ratio versus the cumulative oil production. If we have the progress and the development of the log water oil ratio is going on that particular manner, it can indicate a good reservoir performance. If it produce in an accurate way, it would imply and indicate a poor efficiency and a poor reservoir performance, and the water injection and water flooding should subject to a change, and it has to be an intervention has to be applied. Another sign from of the log water oil ratio, if it was generated on this manner or in this way, so it would inform us that we have a layering effect, where there is a breakthrough that has occurred in a particular layer, and some saturation and satisfaction and of the system. Then this indicates the event where the second layer has breakthrough and the progress and follows the progress, the normal progress of log water oil ratio and the higher water production. So investigating the water oil ratio for a particular well, it fit the performance of log water oil ratio. A breakthrough has happened in one of the layers that is this well is penetrating, and that was a time where there is some increase in the water was occurred at that time. Was also to mention that that well is producing with a high water cut. One of the example also that examinations that should be applied and considered in the practical case is to check the producer well and how the development of the water production and rise up in the water injection is taking place. So this is a chart of that the red one is the oil rate, while the blue one is the water rate, that the water cut percentage. So according to chain plots, it's a very famous chain plot. It's a very famous technique and tactics that would shed a light on the performance of the water injection and show how the performance and how the mechanism of the flood is taking place. Is it via cooling? Is there some channeling? Is there some anomalies and non-justified observation has happened or impacted on your reservoir or not? So giving an insight on the performance or in the chart of the chain plots, this plot that the water oil ratio are being plotted, the normal water oil ratio in the log scale, and the derivative of water oil ratio is also being plotted in the same chart. This signature of water oil ratio with the water oil ratio, the derivative of the water oil ratio, would tell us that there is some possibility of having a channeling and a multi-scale or a multi-layering system. And the advances of the water and the flood front is being developed and being propagated on a layered way. So drawing the water oil ratio and water oil ratio derivative, we got a similar signature of what a chain has explained in his famous type chart. So reviewing another well, that is the water can and that is the oil rate and that is the water production rate, we have got a similar signature of the same signature of the chain has produced. The third well also have the same effect and the same signature. So even the layering was also defined by reviewing the production data and the progress of the water oil ratio by either a chain plot or the normal plot of log water oil ratio. There is some assessment on how to quantify the heterogeneous system. If you have now we understood that we have a layering effect and we have a vertical sweep deficiency, and inefficient flooding is being propagated on the vertical scale, but how to measure and calibrate and to quantify these parameters. In fact, there are several measurements of the heterogeneity. We are gonna just to highlight and review the famous parameters that what we call and it the extraversion coefficient. A extraversion coefficient is just a parameter that can indicate and explain how is the variety and how is the heterogeneity system. So it's simply we are grouping the permeability and ranked it from the upper or the higher permeability and ranked them on as descending order. So leaving the permeability on the top side of the row and doing and generating the cumulative function of the permeability till reach 100% of the total permeability. So by sorting the permeability and drawing the cumulative function of the permeability, we would have this behavior. And the extraversion suggests that if we got the permeability that represent 50% of the system minus the permeability that represent 84% of your system and divided it over the permeability that comes from 50% of your system, it would generate the extraversion coefficient, and that term of the extraversion coefficient represent how much your system is heterogeneous. So just going for, that is a real example of the field, and we plotted and exploited the core data and plotted it after ranking, and we had that line. So with a K50, we got the permeability was estimated as 400 and was 84%. the permeability was read as 148. So this produce and the computation of the Extraversion coefficient 0.64, which represent is not one represent a completely heterogeneous system, 0 represent a homogeneous system. So it's a heterogeneous system and closer to a high heterogeneous system because it's greater than 0.5. So how to exploit the Extraversion coefficient? There is some atypical form of charts that you are having the Extraversion coefficient on y-axis and the mobility ratio on the x-axis, and that curves represent the recovery factor or recovery efficiency with the term, including the term of the water saturation. So, as you know, we estimated the mobility ratio is about 6 of that field, and the Extraversion coefficient represents 0.64. So interception of these two parameters and two factors would projected on this curve that represent the recovery of times the 1 minus initial water saturation that gives 0.05 as a value. So substituting the initial water saturation 0.2, that would produce a 60% as a recovery factor. It's also valuable to point out that these typical charts are designed for a particular water-oil ratio. So it's a specific or a function of a water-oil ratio. So each water-oil ratio would have a different chart and a different arrangement of those curves. So we choose a water-oil ratio of 1 that equates water cut about 50%. So investigating what it will be the situation in case of water-oil ratios become 100 and the water cut is 99.9, which represents the end life of the field. So we choose a plot of water-oil ratio at 100 and using the mobility ratio of 6 along with the Extraversion coefficient of 0.64, we would have the interception of curve of 0.31, and substituting the water saturation, initial water saturation in the equation, we would get a 33%. Now the field is operating about 70% water cut, and as we have pointed out, the recovery factor out to date was 21%. So the real or practical and real actual field performance and actual field givings are pretty closer to the theoretical assumption of the Extraversion coefficient. So this technique would tell us that we will have only 33% after the end of the second recovery and reaching all of our reservoir to 99% of water cut. So this would still tell us that we have much huge oil that left behind, that we should exert a great effort in order to unlock these kind of great reserves and great potential. So that was on the scale of vertical configuration. What it will be the situation in the aerial situation. As we are knowing, that is the reservoir, there is a cross section that was taken across the reservoir from the north to south directions. There are two layers, as we explained earlier. The two layers, the upper layer in some particular wells, they are not is not founded and like benched out, while the lower intervals is existing in most of the well, but still some wells showing a very low net to gross and a great variety in the thickness, but exist in most of the reservoir, while the upper interval having some benching in many wells. That is the same story for a different arrangement and a cross section that cut the reservoir from east to west. The lower interval showing some consistency, although there is some some continuity, but there is some differences in and the variety in the length, while the upper interval show non-continuity. Taking a look on the depositional condition of the reservoir, it follows the deltic environment and the deltic setup where it was deposited on the subfan, deltic subfan. So we have this kind of lens, or this lens, or the lenticular configuration of the reservoir would be formed on this shape. The upper interval is not existing and not is being not encountered in several wells, while the lower interval has some continuity but still variety in the thickness. Also, another investigation. So now it's become like a clear that is we have an areal variety due to the variety in thickness. One layer is completely has a complete change in its thickness, while the lower one has some kind of lateral change. But another investigation was conducted by testing the direction permeability, and we try to understand whether there is some anisotropic system or isotropic system. In fact, by having two core plugs, and we align the direction as from a particular and specific way, and we did a 90% from the over the aerial or the initial direction of the flood front. We found it that is the permeability and even the porosity was changed. The permeability that changed from a particular direction to the 90% direction would have about 20% differences, and that has been founded on the two core plugs test that were carried out on this reservoir. So aside from having a variety in thickness, there is some an isotropic system where the permeability in X is a little bit different from the permeability in Y direction. That would bias the direction of the injection toward the higher permeability directions. So there's an evidence on the poor aerial and lateral sweep efficiency. So before now we have assessed that there is some heterogeneity. The heterogeneity has been assessed and quantified in the producer well and the injector wells, and also in the geological data would support the idea and the confidence about having a heterogeneous system. But now let's see, is it this field is possible and doable for having a polymer injection? One of the crucial element and factors that would define the performance of the polymer flooding is to understand whether you are injecting above or lower the fracture pressure. That requires from your side or from any reservoir engineer dealing with a polymer flooding project to precisely identify the fracture pressure and to evaluate it on an accurate way. It's better to review several ways and several methods of determining the fracture pressure in order to attain a trustable and certain data. One of the methods that we relied on estimating the fracture pressure was dual dipole sonic. Just by we capture several dipole sonic logs, and by generating and estimating the fracture pressure, we found that the fracture gradient is 0.46 psi per foot, while the minimum horizontal stresses, or sometimes being called closure pressure, is 0.43 psi per foot. This is very low values. The formation easy to break down and to fracture. And that what was also calibrated by a fracture job that was carried out in a nearby in a producer well in the field. So this fracture job, the result of it was has been highlighted in the blue table, where it showed the closure gradient 0.49. That is a little bit closer to the one that we got from the log analysis method. Now we moved to the producer itself. If you remember, yesterday we had a discussion about the step rate test, and this is a typical response of the step rate test, where we are injecting different rates, having as we can or as best as we can to equalize the time of each rate, and recording the corresponding or subsequent pressure that is resulted from increasing the injection rate. So by capturing the pressure and the corresponding rate and plotting them, the rate on the in the x-axis and the pressure on the y-axis, we would have and the points that are scattered, and it can be easily distinguished that is there a kind of two straight lines. That one represents a matrix injection, while that line represents a fracture injection mode. The interception will tell us the value of the fracture pressure. So the fracture pressure was 3,200 in that example. This is a bottom hole data, and the fracture gradient 0.45 is very consistent with the data and the results that we got from the fracture job and from the logs. The closure gradient is 0.42. The injectivity index is and that is basically represented by the slope of this curve, is about 1.2 barrel per day per PSI. So we have a good injectivity index, but unfortunately a bad or an adversing fracture pressure value, because it's quite low pressure values, that would minimize the injection profile and the injection pattern of the polymer, because you should keep the polymer below that pressure values. But luckily we have a good injectivity index. Over than 1 is considered as a good or acceptable for a polymer flooding application. Also, we utilized the recorded data, the daily injection data, along with the recorded wellhead pressure for the injection wells, in order to plot and to draw HAL plots. Yesterday we explained that is with the pressure data and the daily rate data, we can estimate and calculate the cumulative rates versus and the cumulative pressure over the time, then use that cumulative rate and that cumulative pressure to plot them and to have the HAL plot. If it has that represents a matrix, has a slope, should be the injectivity index closer to the one that identified by the step rate test. And having the fracture, if it's flattened on that direction, and if it being moving to a vertical direction, it would an indication that there is some introduction and some build up of the plugging, and the scan is being introduced into the injectivity of the well. Fortunately, we got straight lines, which indicates that is most of our injection wells are currently operating in a matrix mode, and we are not or we don't exceed the fracture pressure, and we have this kind of perfectly straight lines that they have even a good match. So we are having a good injectivity index, and at the same time we are injecting less than the fracture pressure. But a caution should be taken toward the injection of the polymer, because we have to understand that is the upper limit of the injection is constrained by the fracture values that are very low indeed. Just having a look on the recorded core, you would find there is some an indication of the softness, and this core indicates friable sandstone with a relatively low cementations, along with some presence of clay content. That data is pretty closer with and pretty similar to the fracture data estimation, and would also support the certainty of the obtained data. So moving to the section of the lab work and how what is the role of the lab analysis in order to optimize the polymer injections. So as we explained, by having the polymer entrained and dropped on the grain surface, we would have a reduction in the effective permeability. So, okay, this is like the example of a real example of the apparatus that is used for measuring the viscosity, a viscometer tool. So, having the viscosity of a different shear rate is being expressed at different polymer concentrations. So this the typical chart and a standard chart of the viscosity of the polymer with the shear rate is being followed the trend, where it's a lower Newtonian, then it becomes like a shear thinning, applying the more shear, it will be having a reduction in the viscosity till get at a very high shear rate, a stabilization in the viscosity. And that's what has discovered in the analysis of the polymer, of the particular polymer type at different polymer concentration. We got that responses. This is a real example that was conducted in NI labs, where the viscosity is being decreased with the rise in the shear rate at different polymer concentration. So in which polymer concentration and polymer viscosity we should operate our polymer flooding, or how we can choose the polymer viscosity or the polymer or either the polymer concentration in order to define it for our field application. So we should list down the parameter of our reservoir and again calculate the permeability ratio, the mobility ratio. And then by having or understanding the range of the shear rate that our fields are operating, so simply how much we are injecting and how much the flood front is being propagated into the reservoir. In our case, we estimated, we found that our field or the field is being undergo 7.2 shear rate and reciprocal seconds. The units of the shear rate is reciprocal seconds. So with this particular shear rate, 7.1 is our reference in order to examine a different polymer concentration. So we picked the polymer, a different polymer concentration and the resulted viscosity of each concentration, and you will plot them on that plot. And then we want to reduce as low as can the mobility ratio. So we choose the viscosity of 7 centibars, or a range from 6 to 8, that achieve a favorable mobility ratio that less than 1. We choose it as like 0.5. Some people would prefer to stick it to 1, but due to a several problem and you don't know effectively and properly what will be the circumstance become due to the efficiency and the degradation of the polymer, the viscosity may be reduced. So at the end, you obtain a 1. But if you designed your field to operate with a mobility ratio 1, with any reason we ignore and we don't count for, maybe that mobility ratio effectively will be greater than 1, so leading to unsatisfactory results. So it's an important part to design your mobility ratio as a safety factor on 0.5, and if it's become 0.5, okay, you will achieve a greater performance. If there is some problems has occurred in your system and your polymer solution, it might return to the one which is still a favorable mobility ratio. So again, expressing the residual factor and the residual resistance factor, we conducted a core flood by flowing the core flood with the water and recording the differential pressure. That is the baseline, how much 0.5 milliliter per minute, that is the rate of the injection of the seawater, was flow through the core plug. And we achieved and we got the stabilizations. Then we started to increase the injection of the water till reaching the 2 milliliter per minute. Then started from that part to inject the polymer. The polymer was injected initially with 0.2, but we found it a high differential pressure. Then we reduced the injection rate of the polymer and reached to a particular value which is 0.2. Then we started later by displacing the water. So this represents the 0.5. So we have to compare that 0.5 with this value, 0.5. So 0.5, the injection rate of the water, comparable with the injection rate of the water, but just prior to the polymer and after, right away after the polymer, we would have a higher differential pressure that was accounting for the polymer retentions. And the ratio between the pressure drop here over the pressure drop here is representing the residual resistance factor. So the water mobility before the polymer over the water mobility after the polymer can be calculated directly by calculating and measuring the pressure drop of the water before and after injecting the polymer. So the initial permeability was about 300 millidarcies. The final permeability that counts for the flooding of the water after the polymer is 6.9. The residual resistance factor is 4. So combining all the previous parameters, relative permeability and the mobility ratio and so on, and drawing the fractional flow curve versus the water saturation in order to predict how it will be the performance of the water flooding, we would have a breakthrough with an average, that is a breakthrough. The breakthrough has been noted by the interception of that line, the conjunction line that started from SCWI. So this represents the water saturation at the breakthrough in the reservoir. So the average water saturation across the whole reservoir is just only 0.32. So with the 0.32 in the all over the reservoir, that would produce a water cut, and the water cut can be reached to 60%. This is a fractional flow, or the water rate and the water fraction over the total fractions. Is different than the water cut, but it can be taken it as like an analogy. So that was actually the case. If you remember the first case where we were reviewing the immediately right away after starting the injection, there was a jump in the water cut and the field were operating with a higher water cut. It's the same, it just validates the same values and the same results that obtained also from the Castro-Patterson. So all the results and the inspection is being aligned, and that would strengthen the confidence and the certainty of the fields that you are dealing with. So that will be the case in case of we are utilizing the polymer with the mobility ratio 0.5. We would have and the breakthrough time would happen as an 0.75% of the average water saturation. Effectively, the water breakthrough time would happen very closer to the residual oil values, that just indicating a very effective and ideal response for an oil displacement. On the contrary, that part of the water flooding indicating that it would be a very long time till reach to the abundant stage, and all that time the field is being producing water cut. But also this would point out that happened on the core scale. So just investigating with this analytical model the performance of the core plug, and this sheds a light on how well or how effectively the polymer will be helpful and will tremendously improve your recovery factors. But might be that will not be actually the case, because the polymer downhole is subjecting towards the degradation. There is some mixing and dilution with the water in the reservoir, and also the reduction of the mobility. So the mobility we are designed and considered in this equation 0.5 may be not the case that is actually being performing downhole in the reservoir. But at the end, you have to work with the theoretical assumption, and in order to, and the benefit of this just model is to see and check whether the polymer is affecting and how much the result would be. So there is really a great differences, and a remarkable gain was attained from applying the polymer. So moving now to how we can change the injection and the selection of injection well, and the strategy of the polymer flooding. Those are the injection wells are injecting, the peripheral injection wells are injecting in the field. We choose the 57 because that well were injecting 4,000 barrels per day, so having a good injectivity index. Because we are subjecting, in case of we shift from a water injection to our polymer injection, we would expect a reduction in the injectivity index, and in turn a reduction in the injection rate. So we constructed a numerical simulation, and we started as I just mentioned, we started with 57 as a reference well, or the polymer well that designed for a polymer injection, in order to sweep all the oil towards the producer. So a different injection strategy, we choose a 2-year of polymer injection followed by a 4-year of injection, and 6 years of polymer injections. Also, we worked on a different polymer concentration. Remember that is the ones that we choose is from 8 to 6, so it should be having a performance lie between those two curves. By introducing the polymer injection with just 4 centiballs for a 6 year of injection, we discovered that this is the baseline of the injection, which represents 4,000. By having and introducing the polymer injection, a reduction in the injection rate will happen due to the effect of the formation residual factor and all the parameters that we already described. And for those 6 years of the injections, then we return back to the water. The impact on the reservoir pressure, unfortunately, it will reduce the reservoir pressure significantly, and in turn there will be some rise up in the reservoir pressure later. How it will be the outcome of terms of a daily oil production rate. So just reviewing the result of the cumulative production, the normal water injection is the green one, the red one is the polymer. So we found it that is for one of the producer well that closer to the injector, due to the fact that we have a reduction in reservoir pressure, it impacting negatively on the cumulative production rate, and the average rate of the oil has been reduced due to the fact that the production rate and the differential pressure as the withdrawal has reduced, and that reduction in the oil rate was not or counted for a longer time, and the gain of the polymer would behave on a very late time or later on in more advanced time, I mean. But the point that we wanted to get a result in sooner as possible in order to evaluate the polymer effectiveness in the field. Also, we found that the same behavior has happened for another reference well, where the polymer, due to the fact we were injecting in less volumes, has reduced the reservoir pressure, consequently reduced the cumulative oil production over in the near future time. It would be a different story in case of we continue with the forecast and the extrapolation. The estimation and the anticipation of the production in a very advanced time, but due to the necessity of having a good and remarkable results in a shorter time, dedicate us to ignore the result and the commencing of the polymer on such a condition. So having and changing the polymer to choose an eighth and was polymer viscosity, it reduced greatly the injection rate, and the same response has happened. An accurate reservoir pressure reduction was noticed, and that has also the same negative impact, and even it become more worse in terms of having a more oil production. So at that time, the injection of the polymer didn't help us in case of we choose it to a peripheral water injection due to several situations and several reasons. So one of the reasons that is the long distance between the injector and the producer wells seems to be too long for correct polymer flooding management. Also, the area represents a good permeability and a good injectivity, but there is some high water saturation or all over and are spread everywhere. The area affected by the polymer flooding or seems to be limited to the near wellbore area even after years of the injections. And in order to see the effect and the impact of the polymer, this required several years of injection in order to have a direct and obvious impact on the oil production in the producer well. So there was a reduction on water injection due to the polymer, as we just pointed out several times, the residual factor and so on. At a state of art, the polymer injection in the peripheral well seems to not be an effective way, and there will not be an additional or incremental recovery would be obtained. But now what will be the situation? Those peripheral water injection well, and that is the water saturation map, and that is the reservoir, where that bottom structure and that is the upper structure. That's part of the oil and oil pools, where it is still having a high oil saturation, and the effect of the injection would not reach to those parts of the field. So the sweep efficiency can be improved, and the change in the injection pattern is suggested. And that drives us to change the injection scheme from a peripheral water injection to a combination, and then by including a dispersed water injection. Yesterday, we explained in details how it will be the change in the situation, and the change in the injection pattern can lead to a positive result and achieve a good optimizations. This is a good example as well of having this kind of strategy. So that place was suggested to be an optimum place where the injection should be placed. So after we placed an injections, that is the start of the injection, and after 2 years of injection, we got that saturation map. After 6 years, and a significant change in water saturation was observed, leading to leaving less bypassed oil, and that is outstanding performance comparable with the peripheral water injection for the same times, whereas some oil bank and the oil volume is left as an bypassed oil volumes. So the dispersed water injection and changing the reservoir, the injection pattern led to an effective and better result. Furthermore, there were an inspection and investigation not only to do a peripheral and dispersed water injection for water only, but also to check what it will be the effect in case of we injecting a polymer. So choosing that well, the new infill well or a new well, the injector well 112-112, we did some sensitivity on the injection rate, a different injection rate. We didn't find any issue in the injectivity. So just injecting with 1,000 barrels per day and keeping the peripheral injection as it is would have that effect on the oil rate production from the all offset wells. So this will be the base case of the only peripheral water injections, the green one, while injecting with 1,000 barrels per day, giving us a higher and a greater effect over injecting 500 and 700 and so on. So that was the case of modeling and seeing the effect of the dispersed water injection and the adding another injection within the middle of the reservoir. It led to achieve a good oil rate and oil recovery. So having and plotting it that the peripheral water injection trend rate versus the time, and the blue line represents the injection rate of 112-112 with just 1,000 barrels per day, and the red one is the injection of the polymer flood, which will be started just after the water pre-flush for about 6 years of injection, then followed and chasing it with driving water to continue the injection. All that oil has been recovered over the just converting the well into injection, and both of them offer a greater recovery over the normal peripheral water injection. So this was a good and ideal example of how the change in the injection pattern and the injection scheme would lead to a good results, and also in this example give to the or shed a light about the effective and adequate reservoir management system by which surveillance has been conducted and performed for the wells in order to tackle the deficiency and to pinpoint the problems. The numerical simulation supported the result and improved the placement of the polymer injection and leading to optimize the polymer flooding and design it on a very effective and well-engineering way. Not only the problem of having a higher oil production and higher cumulative production that resulted from the polymer flooding over normal injection that in turn over the dispersed injection, but also a reduction in the water that can be attained. That is a peripheral injection. The polymer injection, since we choose a peripheral and a dispersed injection and we become closer to the producer well, there is some higher water production and higher water, cumulative water production is being illustrated and forecasted with the red one, but it is still very close to the peripheral water injection and very there is a great contrast between the water injection from 112-112 with the polymer solution. So it means that will be the result in case of we achieved or we just convert and change the pattern and keep it as a water injection, but at the same time we may have a problem of a high water production. But while converting it or doing the dispersed injection on a polymer flood would get a greater cumulative oil and less water production that will be aligned with a successful reservoir development strategy. Finally, the project has started. So as you see, the plant, the schematic of the plant that was designed for this particular project, that is a polymer powder silo. This is a screenshot from the DCS system. that is a blender or hopper that used to accumulate the powder. That is a polymer slicing unit where we are mixing the mother solution, and the polymer maturation tank are responsible for having a stagnant time and stationary time to achieve a good viscosity. The polymer dilution and metering system that comes by the mixing in order to reduce the mother solution or the thick solution to be the final effluent solution that will be injected directly to the wells. And finally, the polymer injection pump that responsible for delivering the final solution, the diluted one, into the wellhead. This is just a small video, a short video showing how is the mother solution look like. So it's a sample of the mother solution. This is a solution of thousands of viscosity, thousands of ppm that represent fairly hundreds of samples. So it moves very slowly. There is a laminarity. There is no turbulence at all. So it's another example and another illustration of the viscous solution. Of course, it offers a higher viscosity relative to the water. And this is a real example of of the polymer that is being captured from the practical application of the polymer injection. So hereby is a structure map of the peripheral well injection well are placed, and that are the producer well surrounding the dispersed polymer injection well. The injection rate is just 1,000 barrels per day. The wellhead pressure is 0. And that was a good point where we are injecting less than the fracture pressure. The average reservoir pressure is 1400 psi. The average injection or injected solution concentration is 1500 ppm. The viscosity target at reservoir condition with this 1500 was 6 centipoise at the shear rate and the temperature of the reservoir. The average injected solution water at the surface is 12. So this is a polymer injection parameter that the bottom hole pressure that would retrieved from a downhole gauges that placed with the within the injection string of the polymer well in order to accurately define and observe the injection behavior. We achieved a stable injection rate and a stable injection pressure performance during the polymer injection. That is a bottom hole pressure. If you remember, this is a chart of residual factors. That is the effect of the polymer, where is a build up and the grow and the differential as long as the slug, the polymer slug is moving and invating and propagating within the reservoir. We obtained a similar and conceptual configurations where that was the baseline of the water injection. And with the commands of the polymer injection, we obtained that performance. This oscillation is related to some stopping and a small troubles that are not important in the injection profile. So finally, I just want to acknowledge and give thanks to the people who helped us to generate and to present this kind of work. And thank you for all for your listening, and hopefully that it become a beneficial and productive for everybody hearing us. Thank you.
Thank you so much, Engineer Mostafa. We all would like to thank you for the amazing webinar. I have received many questions, but I have collected the most important ones. The first question is, how does salinity affect the polymer stability?
Okay, that we already reviewed this effect in one of the charts that demonstrates the polymer stability. It's an experiment where we are conducting the polymer viscosity and measuring the polymer viscosity for a particular concentration or for a different concentration type with a different salinity and with different mixing salinity. So here a chart that on this curve with 1200 ppm, with increasing the concentration, we observed a reduction in the viscosity. The same took place in the case of 800 ppm. So this experiment is an or give an idea about how the performance of the salinity would be with the type of the polymer. And it worth also to highlight that is those type of polymer is resistive for salinity. It would be a very worse for other types of polymer where the deterioration will be more aggressive and the performance or showing a poor performance respect to the effect of the salts. So this
Thank you
will
so
be.
much. Thank you so much for the answer. Someone is asking why we cannot assume the mobility index equal 1, but it's appropriate if it's 0.5. Can't be explained, and it's in the slide that continued concentration versus viscosity plot.
Yes, we already explained and discussed that parameter, and I'm gonna repeat it again. Yes, some people would think, okay, let's choose a 1 and may 1 achieve a good result, but that is on a theoretical basis, because you don't know whether the polymer solution and polymer slug will preserve its continuity and its effectiveness all over the progressing in duration in the reservoir. And the journey of the polymer take place and starting from the mixing unit, following with a pumping scheme, till reaching to the wellhead and along the reservoir, passing through the backers and some restriction in the completion and across the perforation, and then propagating into the reservoir. With all of those passing factors, it would be some deviation from the reality or the ideality, and that would influence on the polymer slug concentration, and the viscosity might subject to a decrease and maybe reduced. So that reduction in the viscosity of the polymer would reduce the effectiveness and the efficiency of the polymer, leading to increase the mobility ratio. If you design it exactly on 1, so maybe actually it will not produce 1, it may be in the downhole or in the reservoir, maybe greater than 1, might be 2 or 1.5 or something in between. So that's what we are saying. It's better as an safety factor to design it less than 1. 0.5 is a good approach that many operators respect and like to follow. 0.7, 0.8 is fine as well, but having this kind of room, it would enable you to inject freely without the stress that is you or fear about your polymer slug that may be deteriorate or diminish in the, its journey toward the displacing front of the oil part. So again, it's a kind of conservativity approach. 0.5 from 1, it's account for any degradation or any problems unforeseen that may take place over the polymer system.
Thank you so much. And the last question is, someone is asking, once the polymer solution mixes with oil and it's produced, how is the separation process at the surface? Does it need special requirements?
Yes, in fact, it require in the case that just we were discussing, there is no polymer has been produced with oil, but some operator are suffering from an issue that is related to the polymer, the presence of the polymer with the oil stream. Some fields show with no problem at all. I mean, they didn't face any troubles in the separation. It depends on the crude oil and in the polymer type and the condition of reservoir pressure and temperature that you are operating. It may have a problem and poses a threat potential for you that requires an additional process and additional items that must be considered during the conditioning of your crude oil. And in some cases, it doesn't have any problem at all. So this thing should be investigated. It requires an advanced, but it's still the thing that you have to deal with. Maybe your analysis showed up that you don't have any problems, then you discover there is some problem that happened to your crude. So it's something that you encountered and then you react accordingly. You may anticipate it, you may take your precautions and all of those things, but it's a quite a challenging thing to track and to evaluate.
Thank you so much, Engineer Mostafa. Thank you. All of the students are thanking you for the amazing webinar you presented. It was really informative. And thank you. I would like to thank all of the students who attended all the webinars and participated in this internship. Thank you so much. And thank you again, Engineer Mostafa, for the amazing webinar.
Thank you. Thank you all.